Now researchers can predict volcanic eruption. Crystal clocks used to time magma storage before volcanic eruptions. The molten rock that feeds volcanoes can be stored in the Earth's crust for as long as 1,000 years, a result which may help with volcanic hazard management and better forecasting of when eruptions might occur. University of Cambridge used volcanic minerals known as crystal clocks to calculate how long magma can be stored in the deepest parts of volcanic systems. This is the first estimate of magma storage times near the boundary of the Earth's crust and the mantle, called the Moho. The results are reported in the journal Science. "This is like geological detective work," said Dr. Ewan Mutch from Cambridge's Department of Earth Sciences and the paper's first author. "By studying what we see in the rocks to reconstruct what the eruption was like, we can also know what kind of conditions the magma is stored in, but it's difficult to understand what's happening in the deeper parts of volcanic systems. Determining how long magma can be stored in the Earth's crust can help improve models of the processes that trigger volcanic eruptions," said co-author Dr. John McLennan, also from the Department of Earth Sciences. The speed of magma rise and storage is tightly linked to the transfer of heat and chemicals in the crust of volcanic regions, which is important for geothermal power and the release of volcanic gases to the atmosphere. The researchers studied the Borgarrón eruption of the Theistereker volcano in northern Iceland, which occurred roughly 10,000 years ago and was fed directly from the Moho. This boundary area plays an important role in the processing of melts as they travel from their source regions in the mantle towards the Earth's surface. To calculate how long the magma was stored at this boundary area, the researchers used a volcanic mineral known as spinel, like a tiny stopwatch or crystal clock. Using the crystal clock method, the researchers were able to model how the composition of the spinel crystals changed over time while the magma was being stored. Specifically, they looked at the rates of diffusion of aluminium and chromium within the crystals and how these elements are zoned. "Diffusion of elements works to get the crystal into chemical equilibrium with its surroundings," said McLennan. "If we know how fast they diffuse, we can figure out how long the minerals were stored in the magma." The researchers looked at how aluminium and chromium were zoned in the crystals and realized that this pattern was telling them something exciting and new about magma storage time. The diffusion rates were estimated using the results of previous lab experiments. The researchers then used a new method, combining finite element modeling and Bayesian nested sampling, to estimate the storage timescales. "We now have really good estimates in terms of where the magma comes from in terms of depth," said Mutch. "No one's ever gotten this kind of timescale information from the deeper crust." Calculating the magma storage time also helped the researchers determine how magma can be transferred to the surface. Instead of the classical model of a volcano with a